Hi everyone, my name is Vildan and I will be presenting our work on an evaluation of situational autonomy for human-AI collaboration in a shared workspace setting. Recent AI systems and robots as their embodied form already help or show great potential to support humans in different domains from work to everyday tasks. There are many application areas that AI systems can potentially be used in, but it's not always clear how to design the interaction with AI systems such that working together with them really leads to better outcomes and task performance compared to the human working alone or with other classical tools. One aspect that can make designing the interaction with AI systems more challenging and different to classical tools is its possible autonomy, so its ability to learn and then make decisions or execute actions automatically and independent from constant human input. Therefore, such potential autonomy of AI systems is an important factor to investigate further and to consider when designing for human-AI interaction. Some previous work already showed that high levels of AI autonomy can be beneficial in complex task settings, but it does not always increase team performance, for example, if the AI could possibly make serious mistakes autonomously. In such cases, humans also do not prefer an AI system to have high autonomy, but rather have no or low autonomy, especially if the errors could occur in high-stakes situations. One way to address these aspects is to implement adaptive autonomy for AI agents, with which they could slide along such an autonomy scale and increase or decrease autonomy depending on the current situation. For instance, if the AI is unsure about doing something, it could decrease its autonomy and ask about it first instead of just executing the action right away. But if it is sure, again, it could go up in autonomy, for example. While such adaptive autonomy has been deemed promising by previous work and is often desired by humans if they're asked, there is a lack of empirical evaluation for settings in which an AI changes its autonomy automatically and depending on the situation while collaborating with a human on a task together. However, it is crucial to empirically evaluate the actual effects of AI autonomy adaptation within human-AI collaboration to ensure a validated human-centered approach for the development of future AI systems. Therefore, we investigate this with two research questions. First, we examine what happens when an AI teammate automatically switches its autonomy depending on the situation while working together with a human partner to solve an overall team task in a shared workspace. Additionally, we investigate how our participants perceive the different agents with varying autonomy degrees and the adaptive one, as well as the interaction with them. For our experiment, we used this task setup. We designed a computer game in which there is a shared office space. The task of the human AI team is to successfully organize the content of the boxes at the top, which are filled with books and different types of documents. As shown right now, to successfully organize a document, it needs to be picked up, processed at its processing station, and put into a folder. Finally, the folder needs to be labeled with the correct color and then stored into the folder shelf. To organize the books, the human can either hand over a book to the agent such that it can be put into the bookshelf, or they can pick up a book themselves and bring it to the bookshelf as well. Periodically, as shown right now in the video, the doorbell rings visually and a timer starts. This delivery of a new box needs to be accepted before time runs out, such that the contents of the boxes are filled up again and the team can continue to work on as many documents and books as possible. For each successfully sorted folder or book, the team receives a reward of 5 points. So the overall task goal of the human AI team is to organize as many document folders and books as possible in a given time. Based on the rewards they were able to collect in that time, we calculate the overall team performance score. As you already saw in the video, some parts of the task can only be completed by the human, for example, the document processing. Other subtasks can only be completed by the agent, for example, bringing over the label. And some subtasks can be done by both teammates, for example, accepting the delivery. Here on the right, a list of all subtasks and who can complete them is shown. Such a task division means that the team really needs to coordinate well for the best possible performance, as some subtasks require interdependent steps from each teammate to be completed. And different ways to coordinate within the team can be more or less efficient. As you can see at the bottom, for the interaction within the team, the agent can communicate with the human by showing messages, and the human can give commands to the agent at any given time during the trials. Also, during the experimental trials, our participants had a limited field of view such that they could not always see the entire workspace. As shown in the video right now, for instance, they do not see what happens behind them. So this is the task setup we use to investigate how well the collaboration within the human AI team works in our different experimental conditions in which the agent has varying autonomy levels. Depending on the autonomy level of the agent, it initiates interactions with the human in different ways. So how the agent communicates with the human is determined by it. The different possible autonomy levels we define in our task are high, moderate, low, and no autonomy. These autonomy levels, as well as the current state of the workspace environment, and depending on the human input, the agent always chooses its next action that it considers to be the next best thing to do in each type of situation. While this was a general overview of how the agent selects its action, please refer to our paper for the proper formalization and all details about it. So the action selection of our agent not only depends on its autonomy level, but also on the current situation. For agents to react appropriately to different kinds of situations, we identified general situations that can typically occur during collaboration in shared workspaces. There are 3 types of situations we identified to be important in our task. However, they could also be transferable to other tasks in shared workspace settings, and systematically identifying them is an important contribution of our work. You can find all situation types in our paper. But one example is the occurrence of a higher priority event that could be addressed by the agent. In our setting, that means, for example, while the agent is sorting books, the doorbell rings and a delivery has to be accepted. For each autonomy level, we then define behaviors and communications with the human to address the situation. Here, an example is shown for when the agent is on high autonomy. It is currently sorting books and recognizes that the doorbell is ringing. Therefore, it briefly interrupts the book sorting to accept the delivery. It informs the human teammate of this action by showing a corresponding message. This was done because the agent knows that the acceptance of the deliveries is more important right now to ensure that more books and documents are available to organize and more points can be scored by the team overall. But since we not only want to investigate the effect of such fixed autonomy levels, but also compare them to what happens when an AI agent can switch between them automatically depending on the situation, we derive criteria for how such a switch should occur. First, for instance, whether the agent is sure what to do can have an influence on whether it should exhibit higher or lower autonomy. The effect of a potential failure to complete a task can also have an effect. That means, for example, if an error that a highly autonomous agent could make is very bad in the current situation, then adjusting its own autonomy to be lower in that case could be beneficial. A theory of mind about the human or a belief about what the human partner can see and currently knows should be considered as well. For instance, if the human is turned away from the doorbell and doesn't see it, and the agent knows that, it could increase its autonomy to accept the delivery autonomously rather than the team missing out on it. If a task could be completed by both teammates, comparing whether it is better executed by the agent or the human could also be considered. And lastly, whether the agent would ask the human to change their behavior can also be important. If it makes sense in the current situation, the agent with higher autonomy could make suggestions for the human to change actions in order for the team to complete the task better together. All of the criteria were derived from literature as well as a pre-study we conducted in our task setup. And with such insights, we identify all these factors to contribute to the adaptation of the AI autonomy level. The switch in autonomy between the defined levels and the resulting current level is the basis for how the agent chooses its next action. From these criteria, we then define specific heuristic rules that apply in our task such that the switch between the levels can be implemented and the agent behaves accordingly. Please refer to our paper for details on all implemented rules. However, here one example is shown of a specific rule for a general situation type, in this case, a higher priority task arising. The human is currently providing books such that they are accessible to the agent. Since the agent is currently on high autonomy, it directly picks them up and organizes them into the bookshelf. During the book sorting, the human picks up a document and thus the agent recognizes that they will need a label for it. But it is very unsure about recognizing the color correctly, so it switches to low autonomy and asks the human what to do. The human can then select an action that is currently possible to execute for the agent. The aim of such a switch from high to low autonomy is to avoid a mistake of the agent, as remaining on high autonomy and possibly bringing over a label of a wrong color, which the human would then have to dispose of, would actually cost time. So instead, the agent decreases its autonomy and asks about what to do next and waits for the human input. So with the definition for the fixed and adaptive autonomy levels, we conduct experiments to answer our research questions. First, we want to know how situational autonomy adaptation influences the overall team performance compared to the fixed autonomy levels. And second, we investigate how the participants perceive the agent in their condition and the interaction with it. To do this, we conduct an experiment with 50 participants in a between-subject design. We have 5 conditions, 4 for the fixed levels of no, low, moderate, and high, and 1 for the adaptive autonomy. Each of them have 10 participants who all completed 3 trials of 8 minutes each. From this data, we calculate the average performance scores. At the end, we also asked all participants about their experiences with the agent of their condition and the interaction with it in questionnaires. All detailed results can be found in the paper, but generally we find that the overall team performance was the highest on average in the adaptive autonomy condition. Specifically in some subtasks that are related to the performance, like for instance the number of accepted deliveries, there is a significant difference between the no, low and moderate conditions compared to the adaptive one. Also, generally the adaptive agent was also perceived as helpful. And while the high autonomy agent was perceived as the most autonomous of the agents, the adaptive agent was perceived as the most intelligent agent to work with. This could indicate that merely having highly autonomous agents is not necessarily always positive, but rather that adjusting autonomy and thus sometimes decreasing it to avoid making mistakes, for instance, as we did here, could be the best option for an AI teammate. So overall, we propose a cooperative task in a simulated shared workspace in which we investigate how different autonomy levels and their adaptation influence task performance and human perception of the AI agent. We derived criteria for implementing the switch of autonomy levels and defined specific rules for the adaptation of AI autonomy in our task. We then ran experiments which showed that there are benefits in terms of both performance and how the agent is perceived when it adapts its autonomy depending on the situation. And while the situation types we investigate are not necessarily exhaustive, they can also occur in other shared workspace settings because we consider general aspects like higher priority subtasks arising or errors or uncertainties occurring. So we believe that our work could be transferable to implement situational autonomy adaptation in other tasks as well. Generally, we hope that these empirical insights could help to inform the design of future AI systems and lead to more beneficial and seamless human-AI cooperation in shared workspaces. Thank you for listening, and if you want more information or details, you can refer to our paper.